We often marvel at the vastness of the universe, with its countless stars, galaxies, and nebulae stretching out into the infinite expanse. But what if this seemingly stable cosmic structure isn't as permanent as we think? What if the universe itself could be torn apart, with even the smallest particles of matter being ripped asunder? This is the unsettling yet fascinating concept of the Big Rip, a hypothetical scenario that envisions the ultimate fate of the universe as a violent and catastrophic event. In this video, we'll delve into the science behind the Big Rip, exploring the theoretical framework, the underlying forces at play, and the potential timeline of this cosmic cataclysm. We'll examine the role of dark energy, the mysterious force that seems to be accelerating the expansion of the universe, and its potential to eventually overcome the fundamental forces that hold matter together. Whether you're a cosmology enthusiast, a science fiction fan, or simply someone who ponders the big questions about the nature of existence, this exploration promises to challenge your understanding of the universe's ultimate fate and spark a deeper appreciation for the delicate balance of forces that make our existence possible. And who knows? Maybe the next big discovery about the Big Rip will be made by someone watching this video right now. The answer to these cosmic mysteries may not lie in textbooks or observatories, but in the depths of your own curiosity and imagination. The Big Rip is a hypothetical cosmological model that paints a dramatic and violent picture of the universe's ultimate fate. In this scenario, the expansion of the universe accelerates at an ever-increasing rate, eventually tearing apart everything in existence, from galaxies and stars to atoms and even the very fabric of space-time itself. This catastrophic event is driven by dark energy, a mysterious force that seems to be accelerating the expansion of the universe. In the Big Rip scenario, dark energy becomes so dominant that it overwhelms all other forces, including gravity, electromagnetism, and the strong and weak nuclear forces. The standard model of cosmology predicts that the universe will continue to expand but at a relatively constant rate. However, the Big Rip scenario posits a different outcome, where the expansion accelerates exponentially, driven by an ever-increasing amount of dark energy. As this expansion accelerates, the distances between galaxies and stars will grow rapidly. Eventually, the gravitational pull holding galaxies together will be overcome, and they will be torn apart. This process will continue on smaller and smaller scales, with stars being ripped away from their planets, planets being shredded, and eventually, even atoms and subatomic particles being torn asunder. The final stage of the Big Rip is a singularity, a point in time where the universe's density and temperature becomes infinite and the laws of physics as we know them break down. This singularity, often called the Big Rip singularity, marks the end of the universe as we understand it. However, it's important to note that the Big Rip is just one possible scenario for the universe's ultimate fate. It requires the existence of a hypothetical form of matter called phantom energy, which has unusual and somewhat implausible properties. Current observations and measurements suggest that the Big Freeze, where the universe expands and cools indefinitely, is a more likely outcome. Despite its speculative nature, the Big Rip remains a fascinating and thought-provoking concept. It pushes boundaries of our understanding of the universe and raises profound questions about the nature of dark energy, the ultimate fate of matter, and the potential for a catastrophic end to all existence. The plausibility of the Big Rip hinges on the specific type of dark energy present in our universe. A particular form of dark energy known as phantom energy, which increases in density as the universe expands, could potentially trigger this catastrophic event. The key factor in determining whether the Big Rip will occur is a value called the equation of state parameter, denoted by the letter W. This parameter describes the relationship between the pressure and energy density of dark energy. If the value of W is greater than -1, the expansion of the universe will accelerate, but dark energy will dissipate over time, and the Big Rip won't happen. However, if W is less than -1, as is the case with phantom energy, the density of dark energy will increase as the universe expands, eventually overpowering all other forces and leading to the Big Rip. Scientists have developed an equation known as the Big Rip equation to calculate the estimated time from the present to the Big Rip. This equation takes into account factors like the current value of the Hubble constant, which measures the rate of expansion of the universe, and the density of all matter in the universe. While the exact value of W is still uncertain, current observations suggest it's close to -1, but not quite below it. This means that the Big Rip is not definitively ruled out, but it's also not an immediate threat. If future observations determine that W is indeed less than -1, the Big Rip equation can help us estimate when this catastrophic event might occur. The Big Rip equation, while complex in its mathematical formulation, provides a crucial tool for scientists to assess the likelihood of the scenario and to understand the potential implications of dark energy for the ultimate fate of the universe. To illustrate the potential consequences of the Big Rip, the scientists who proposed this hypothesis represented a hypothetical scenario based on specific values for the equation of state parameter, the Hubble constant, and the density of matter in the universe. In this scenario, the Big Rip would occur approximately 22 billion years from the present. This might seem like an unimaginably distant future, but it's a sobering reminder of the potential impermanence of even the largest cosmic structures. Leading up to the Big Rip, a cascade of catastrophic events would unfold. Roughly 200 million years before the final singularity, galaxies would begin to drift apart from one another, their gravitational bonds weakening as the expansion of the universe accelerates. About 60 million years before the end, gravity would become too weak to hold galaxies together, causing them to disintegrate into their constituent stars. Planetary systems, like our own solar system, would then become unbound, with planets hurtling away from their parent stars into the ever-expanding void. As the Big Rip approaches, the destruction would accelerate exponentially. In the final minutes, stars and planets would be ripped apart, and even atoms themselves would be torn asunder. The very fabric of space-time would be shredded, and all distances would diverge to infinity. This chilling scenario, while hypothetical, serves as a stark reminder of the potential power of dark energy and the fragility of the universe as we know it. While the likelihood of the Big Rip occurring is still uncertain, it challenges us to contemplate the ultimate fate of the cosmos and the potential for a catastrophic end to all existence. While the Big Rip scenario is theoretically possible, current observations of our universe suggest that it's not the most likely outcome. The value of the equation of state parameter, which determines the behavior of dark energy, appears to be very close to -1. This value of state parameter is crucial because it's the dominant term in the Big Rip equation. The closer W is to -1, the further into the future the Big Rip would occur. If we were exactly -1, the Big Rip would be impossible, regardless of other factors like the Hubble constant or the density of matter in the universe. However, current cosmological data, while suggesting that W is close to -1, still contains some uncertainties. These uncertainties make it difficult to definitively determine whether W is slightly above, below, or exactly equal to -1. Moreover, due to statistical fluctuations in measurements, it's nearly impossible to measure W with absolute precision. This means that even if future observations narrow down the range of possible values for W, it's unlikely that we'll ever be able to definitively rule out the Big Rip. In essence, the closer the measured value of W gets to -1, the further the Big Rip is pushed into the future. The universe is alive. It's a place of constant motion and change, where stars are born, galaxies collide, and black holes devour matter with insatiable hunger. What if this cosmic dance eventually winds down? What if the universe's ultimate fate is not a fiery explosion or a grand collapse, but a slow and chilling fade into darkness? This is the prospect of the Big Freeze. A cosmological scenario where the universe continues to expand forever, growing colder, darker, and emptier with each passing eon. Imagine a universe where stars eventually burn out, galaxies drift apart, and the very fabric of space-time stretches into a vast, empty expanse. In this video, we'll explore the science behind the Big Freeze. We'll delve into the concepts of entropy, dark energy, and the accelerating expansion of the universe. The foundation of the Big Freeze lies in a fundamental law of physics, the second law of thermodynamics. This law tells us that in any isolated system, like our universe, things tend to go from order to disorder over time. This chaos is called entropy. Entropy is a measure of disorder or randomness. The second law of thermodynamics says that the total entropy of the universe can only increase. This means that energy over vast stretches of time will become more and more spread out and diluted, like a cup of coffee gradually cooling down as its heat dissipates into the surrounding air. Now, imagine this happening on a cosmic scale. Stars burn out, their energy dispersing into the vastness of space. Galaxies drift further and further apart, becoming isolated islands in an ever-expanding sea of darkness. Eventually, all the energy in the universe will be evenly distributed, and there will be no more fuel to drive any processes, no more stars to ignite, no more planets to form. This is the state of thermodynamic equilibrium, the ultimate heat death of the universe. The idea that the universe might eventually become too cold to support life isn't new. Way back in the 18th century, a French astronomer named Jean-Sylvain Bailly imagined planets gradually cooling down over time, some becoming too cold to sustain life. He called this final state of the universe equilibrium, where all motion and activity cease. In the 19th century, Lord Kelvin, a brilliant physicist, took this idea further. He theorized that all the mechanical energy in the universe would eventually dissipate into heat, leading to a state of maximum entropy where nothing could happen anymore. Kelvin's ideas were further developed by other scientists, like Hermann von Helmholtz and William Rankine, who explored the implications of this heat death for the fate of the universe. Their work laid the foundation for our modern understanding of the Big Freeze. But here's the thing. The Big Freeze isn't just about the laws of thermodynamics. It's also intertwined with the expansion of the universe and the mysterious force known as dark energy. Back in the 19th century, Lord Kelvin was grappling with the nature of heat and energy. He realized that heat wasn't some mysterious substance, but a form of mechanical energy, like the energy of motion. In 1852, Kelvin published a groundbreaking paper where he outlined the second law of thermodynamics. This law, in simple terms, says that energy tends to spread out and become less useful over time. Think of it like a ball rolling down a hill. It loses its potential energy as it rolls, and eventually, it comes to a stop at the bottom. Kelvin applied this idea to the entire universe. He imagined a future where all the energy in the universe would eventually become evenly distributed. In this state, there would be no more energy differences to drive any processes, no more stars to shine, no more life to exist. He called this the heat death of the universe, a state of universal rest and death. This idea was a radical departure from the prevailing view of an eternal and unchanging universe. It sparked intense discussions with other scientists, like William and Hermann. In 1862, Kelvin published another paper where he clarified his vision of the universe's ultimate fate. He described a state where all available energy is converted into unusable heat, leading to universal stagnation and the end of all physical phenomena. But Kelvin also recognized a paradox. If the universe were infinitely old, as many believed at the time, it should have already reached this state of heat death. The fact that stars still shine and the universe is still dynamic suggests that it had a beginning, a starting point from which energy began to dissipate. This paradox challenged the prevailing understanding of the universe's age and origins, paving the way for new cosmological models like the Big Bang Theory, which proposes a finite age for the universe in that it's dynamic and evolving. Kelvin's ideas painted a bleak picture for the universe's ultimate fate. The Big Freeze, as we understand it today, is a descendant of this heat death concept. Now, where do we stand today with this whole Big Freeze idea? Well, it's complicated. Our current understanding is tied to our assumptions about the ultimate fate of the universe. Think of it like this. We have different maps of the universe, and each map shows a slightly different path to the end. Some maps suggest that the universe is open or flat. This means it will just keep expanding forever, like a balloon that never stops inflating. In these scenarios, we have two possible endings: the Big Freeze or the Big Rip. The Big Rip is a pretty wild idea, and I did talk about it in another video. It suggests that the expansion of the universe will get so fast that it will eventually tear everything apart, from galaxies and stars down to atoms and even the very fabric of space itself. It's like the universe stretching itself into oblivion. If you'd like to learn more about the Big Rip, I encourage you to watch my previous video, which I'll link in the description below. But let's get back to the Big Freeze. If a special number called the cosmological constant is 0, then the universe will keep expanding and cooling down until it reaches the coldest possible temperature, absolute 0. However, our current observations suggest that this cosmological constant is not 0. It's actually positive. This means the universe won't reach absolute 0. Instead, it will approach a slightly warmer temperature, but it will still end up in a state where everything is spread out and there's no more usable energy to do anything interesting. Think of it like a battery that's almost, but not quite, empty. It can't power anything anymore, even though it still has a tiny bit of charge left. This is the kind of heat death we might be facing, where the universe reaches a state of maximum entropy. So even with the positive cosmological constant, the big freeze is still a plausible outcome. The universe will keep expanding and cooling down, and eventually it will reach a point where all the energy is so spread out that it's useless for doing any work. Imagine a clock that ticks not in seconds or minutes, but in trillions upon trillions of years. That's the kind of timescale we're dealing with when we talk about the big freeze. It's a future so distant that it's almost impossible for our human minds to grasp. Right now, the universe is still a pretty lively place. We have stars blazing with energy, galaxies swirling with matter, and all sorts of cosmic activity happening. But if the big freeze is real, this is just a temporary phase. Over immense stretches of time, stars will exhaust their fuel and burn out. They'll leave behind remnants like white dwarfs, neutron stars, and black holes. Even the most massive black holes will eventually evaporate, disappearing into a puff of Hawking radiation. As the universe keeps expanding, the remaining matter will become incredibly spread out. The overall energy density of the universe will decrease and everything will gradually cool down. If the cosmological constant is zero, the temperature will eventually approach absolute zero. But if the cosmological constant is positive, as current evidence suggests, the temperature will level off at a slightly warmer value. Either way, the universe will enter what's called the dark era. It's a bleak picture, a dilute gas of photons and leptons, elementary particles like electrons and neutrinos scattered across an unimaginably vast and empty space. Activity will dwindle to almost nothing, with incredibly low energy levels and timescales that make billions of years seem like the blink of an eye. Perhaps the universe will experience another inflationary epoch, a sudden burst of expansion that changes everything. Or maybe the current vacuum state, the underlying energy of space, will decay into a lower energy state, altering the course of events. And then there are also those truly mind-boggling theories that suggest that over incredibly long periods, entropy might spontaneously decrease. Imagine the universe creating a new universe from the remnants of the old. But the timescale for such an event is so vast that it's almost beyond comprehension. Not everyone agrees that the Big Freeze is the inevitable fate of the universe. There are some scientists and philosophers who challenge the very foundation of this idea, questioning whether we can even apply the concept of entropy to the entire universe. Max Planck, one of the pioneers of quantum mechanics, argued that the phrase entropy of the universe is meaningless because we can't precisely define it. It's like trying to measure the size of the ocean with a teaspoon. It just doesn't make sense. Other scientists have raised similar concerns, that our understanding of the universe is still incomplete, and trying to apply thermodynamic principles to a system that has never been in equilibrium is problematic. Laszlo Tisza, a physicist, argued that we can't argue about entropy for a system that's not in equilibrium. It's like trying to measure the temperature of a pot of boiling water while it's still on the stove. The reading will keep changing. Hans Adolf Buchdahl criticized the assumption that the universe can be treated as a closed thermodynamic system. He argued that we need to consider the universe's dynamic nature and its potential interactions with other universes or dimensions. Even the very definition of entropy for systems that are not in equilibrium is still debated. Some physicists acknowledge the widespread belief in non-equilibrium entropy but admit that it's difficult to define rigorously. Peter Landsberg, a physicist and educator, expressed skepticism about applying thermodynamics to the entire universe without further investigation. He considered the answers to such questions speculative rather than definitive. A 2010 analysis of entropy further highlighted the challenges in quantifying gravitational entropy, suggesting that the observable universe may have more entropy than previously thought, with supermassive black holes being the largest contributors. Lee Smolin, a theoretical physicist, takes a different approach, arguing that gravity actually prevents the universe from reaching thermal equilibrium. He points out that gravitationally bound systems, like stars and galaxies, have a unique property. Their components' velocities increase as energy is removed. This means that these systems don't tend towards a homogeneous equilibrium state, but instead become more structured and heterogeneous over time. Recent experimental findings support this perspective, demonstrating the existence of stable non-equilibrium steady states in relatively simple closed systems. These findings suggest that an isolated system fragmented into subsystems might not necessarily reach thermodynamic equilibrium and could instead persist in a non-equilibrium steady state. The universe, as we currently understand it, exploded into existence with the Big Bang, and it's been expanding ever since. Galaxies are hurtling away from each other, and space itself is stretching like a cosmic rubber band. But what if this expansion isn't the end of the story? What if the universe's ultimate fate is a dramatic U-turn, a collapse back into itself in a fiery inferno? This is the mind-blowing idea behind the Big Crunch. A scenario where the universe's expansion slows down, stops, and then reverses, pulling everything back together in a catastrophic collision. The story of the Big Crunch begins, surprisingly, with the question posed to the great Isaac Newton way back in the 17th century. Richard Bentley, a scholar and churchman, was preparing a lecture about Newton's theories and their implications for the existence of God. He wrote to Newton with a question that would become known as Bentley's paradox. Bentley asked, if the universe is finite and all the stars attract each other through gravity, wouldn't they eventually collapse into a single point? And if the universe is infinite with infinite stars, wouldn't the infinite gravitational forces tear all the stars apart? It was a simple question with mind-blowing implications. It challenged the very foundation of Newton's theory of gravity, suggesting that a universe governed by gravity couldn't be stable. It would either implode or explode. This paradox, in a way, foreshadowed the Big Crunch theory, hinting at the possibility of a universe collapsing under its own weight. But back then, people thought of stars as fixed points in space, not the dynamic moving objects we know them to be today. We now know that stars are constantly in motion, orbiting the centers of galaxies and moving through the vast expanse of space. This motion counteracts the pull of gravity, preventing the universe from collapsing in on itself, at least for now. But the question of the universe's ultimate fate remained open. Could gravity eventually win the tug of war, pulling everything back together in a big crunch? Or would the universe continue to expand forever? Albert Einstein initially thought the universe was static and unchanging. In 1917, he teamed up with Dutch astronomer William de Sitter to see if his theory of general relativity could support this idea. De Sitter crunched the numbers and found that Einstein's equations could indeed describe a simple, unchanging universe. This led many scientists to believe that this static model was the correct picture of the universe. But there was a problem. Einstein's theory of general relativity, while allowing for a static universe, also described a universe that was inherently dynamic, prone to change and motion. This contradicted the observations at the time, which suggested a stable and unchanging universe. Einstein realized that to keep a static universe from collapsing under its own gravity, he needed to introduce a new force, an anti-gravity force that would counteract the pull of gravity. He called this the cosmological constant, and it was basically a fudge factor he added to his equations to make them fit the observations. But this cosmological constant was a bit of a thorn in Einstein's side. There was no observational evidence for it, and it made his elegant equations more complicated. The static universe model was eventually blown out of the water by Edwin Hubble's groundbreaking observations at the Mount Wilson Observatory. Hubble was a meticulous astronomer who carefully measured the distances to various galaxies. He combined his findings with the redshift measurements of Vesto Slipher and Milton Humason. Redshift is like a cosmic Doppler effect. It's when light from distant objects gets stretched, making it look more red. This redshift tells us that those objects are moving away from us. Hubble's analysis revealed a mind-blowing pattern. The further away a galaxy is, the faster it's moving away from us. This relationship, known as Hubble's law, was the first real evidence that the universe was expanding, a discovery that completely changed our understanding of space. Hubble's initial calculations were a bit off, but his main finding was spot on. The universe wasn't static, it was expanding like a motherfucker. This discovery shattered the idea of a static universe and made Einstein's cosmological constant unnecessary. It also kicked off a new era of cosmological research, leading to the development of the Big Bang Theory and other models that describe the universe's evolution. Einstein famously called the cosmological constant his biggest blunder, regretting his attempt to force a static model onto a dynamic universe. With Hubble's law shaking up the world of physics, Einstein had to admit that his biggest blunder was no longer needed. The universe wasn't static, it was expanding, and there was no need for a fudge factor to keep it from collapsing. Einstein even visited Hubble at the Mount Wilson Observatory to thank him for basically proving him wrong. It was a big moment in science, showing that even the greatest minds can be wrong, and that new discoveries can completely change our understanding of the universe. With the expansion of the universe confirmed, both Einstein and Newton's ideas about a static or contracting universe went out the window. Scientists started to embrace the idea of a dynamic and evolving universe, leading to the development of the Big Bang Theory and other models that describe how the universe has changed over time. The Big Crunch, while a dramatic and captivating idea, might not be the only way the universe could end in a fiery collapse. It sparked another intriguing concept, the cyclical universe, also known as the Big Bounce. Imagine a universe that's not just expanding, but also contracting. In this scenario, the Big Crunch isn't the end, but rather a transition, a turning point that leads to a new Big Bang and a fresh start for the universe. With the universe expanding and contracting, creating and destroying in an endless cycle of renewal. Our current universe, in this view, is just one iteration in an infinite chain of universes, each with its own unique properties and stories to tell. This cyclical view of the universe challenges our traditional understanding of time, where there's a clear beginning and end. Instead, it suggests a continuous loop, a cosmic Groundhog Day where the universes keep repeating itself, but with variations and surprises in each cycle. Even Albert Einstein briefly considered this idea back in 1931. He imagined a universe that existed before the Big Bang, undergoing a previous cycle of expansion and contraction. He even entertained the possibility that the cycle could repeat infinitely. While Einstein eventually moved on from this idea, other scientists and cosmologists have continued to explore the concept of the cyclic universe. Some models suggest that the universe might go through a series of bounces, with each bounce leaving behind subtle clues or remnants that we might be able to detect through observations. The Big Bounce concept has also been explored in more recent cosmological models, such as the Ekpyrotic theory. This theory, developed by Paul Steinhardt and his colleagues, offers a different take on the cyclical nature of the universe. Instead of a traditional Big Crunch followed by a Big Bang, the Ekpyrotic model suggests that the Big Bang was the result of a collision between two parallel universes or branes in a higher dimensional space. Our universe exists on one of these branes, and when it collides with another brane, it's like a cosmic fender bender that triggers a new Big Bang. In this scenario, the collision of the branes is like the Big Crunch, marking the end of one cycle and the beginning of another. The matter and radiation we see today are remnants of quantum fluctuations that happened before the collision. It's like the debris left over from the cosmic crash. According to the Ekpyrotic model, our universe will keep expanding for billions of years, but eventually it will start to contract. This contraction will lead to another brane collision, another Big Bang, and a fresh start for the universe. The Ekpyrotic theory has some advantages over earlier cyclical models. It addresses some of the problems associated with the Big Crunch, like why the universe appears to be so flat and why we don't see certain types of particles called magnetic monopoles. These problems are resolved by the presence of dark energy, which in the Ekpyrotic model is explained as the force between the branes. The Ekpyrotic model also allows for an infinite number of cycles in both the past and the future. This means the universe might have no beginning or end, just an endless cycle of expansion and contraction. But the Ekpyrotic theory has its own challenges. The concept of branes, which is central to the theory, is still not fully understood within string theory, which is a theoretical framework that tries to unify all the forces of nature. There are also concerns about whether the patterns of density fluctuations in the early universe, which are important for explaining the formation of galaxies and other structures, could survive the Big Crunch. The conformal cyclical cosmology model, proposed by physicist Roger Penrose, offers a mind-bending twist on the idea of a cyclical universe. It suggests that the universe goes through endless cycles of expansion and contraction, but with a unique mechanism that sets it apart from other cyclical models. Imagine a universe that expands and expands, eventually reaching a point where all matter decays and transforms into light. In this state, with no mass or distance scales left, the universe becomes indistinguishable from the initial conditions of the Big Bang. It's like the universe hits the reset button, erasing all the structures and complexities it has built up over billions of years. This reset effectively creates a kind of Big Crunch, but instead of a fiery collapse, it's a smooth transition into a new Big Bang, starting a fresh cycle of expansion. This model addresses a problem that plagues many traditional Big Crunch scenarios: the buildup of entropy, or disorder. In the CCC, the decay of matter into light resets the entropy clock, preventing the universe from reaching a state of maximum chaos and allowing for a new cycle to begin. Penrose and his colleague Vahe even suggested that we might be able to find evidence for the cyclical cosmology in the cosmic microwave background radiation, or CMB. They predicted that specific patterns in the CMB, like concentric rings with uniform temperature, could be the remnants of gravitational waves from supermassive black hole collisions in the previous cycle of the universe. However, as of 2020, these predicted signatures haven't been found in the CMB data. This casts some doubt on the specific predictions of the CCC, but it doesn't necessarily rule out the entire model. Critics of the CCC have also raised concerns about the requirements for all particles to lose their mass as the universe ages, a condition necessary for the universe to return to its initial state and trigger a new Big Bang. But Penrose has countered these criticisms by pointing to other evidence for CCC, like concentric rings in the CMB that he believes are not random fluctuations, but specific patterns caused by gravitational waves from the previous cycle. Loop quantum cosmology, or LQC for short, is a fascinating approach to understanding the universe that challenges some of the traditional ideas of the Big Bang. It's based on a theory called loop quantum gravity, which suggests that space and time aren't continuous, but are actually made up of tiny, discrete chunks like pixels on a screen. Now, in the standard Big Bang model, the universe starts from a singularity, an infinitely small and dense point. But LQC says, hold on a minute, that doesn't make sense. It proposes that instead of a singularity, there was a quantum bridge between a contracting universe and an expanding universe. Imagine the universe like a bouncing ball. It contracts, reaches a certain point, and then bounces back, expanding again. This bounce is driven by quantum geometry, the idea that space and time are quantized at the smallest scales. It introduces a new force that prevents the universe from collapsing into a singularity, causing it to bounce back instead. This resolution of the singularity has some mind-blowing implications. It challenges the idea that the Big Bang was the absolute beginning of the universe, suggesting that there might have been something before. It also opens up new possibilities for exploring the very early universe, the period right before and after the bounce. To study this quantum bounce, scientists use a simplified framework called the effective dynamics approach. It's like using a simplified map to navigate a complex city. It might not show every detail, but it gives you a good overall picture. Numerical simulations have shown that this effective dynamics approach works pretty well in most cases, providing a good approximation of the full loop quantum dynamics. But there are some limitations. In situations where quantum fluctuations are very large, the effective dynamics might not be completely accurate. Despite these limitations, LQC offers a compelling alternative to the traditional Big Bang cosmology. It resolves the singularity problem, provides a natural mechanism for inflation, which is that period of rapid expansion in the early universe, and opens up new avenues for exploring the universe's past and future. While current observations suggest a big freeze scenario, where the universe keeps expanding and cooling down, some interesting possibilities emerge from certain physical theories. If a special type of dark energy called quintessence is the main driver of the universe's acceleration, and if our current observations about dark energy are correct, a surprising twist could occur. The accelerating expansion we see today might actually reverse within the next 100 million years, leading to a phase of contraction. This scenario, proposed in a study by Anna Ehis and Paul Steinhardt, aligns with cyclical models of the universe and recent theories in quantum gravity. This study suggests that the universe could enter a phase of slow contraction that lasts for about 1 billion years before transitioning back into a new phase of expansion. This possibility challenges the traditional view of a linear timeline for the universe, where it just keeps expanding forever. Instead, it opens the door for a cyclical model, where expansion and contraction alternate in a never-ending dance. While the Big Crunch might not be the most likely ending for our universe, it's still a mind-blowing scenario to consider. Physicist Paul Davies has painted a vivid picture of what might happen if the universe were to collapse back in on itself, and let me tell you, it's not pretty. Imagine a universe that's like a runaway train, hurtling towards a head-on collision. Galaxies would start crashing into each other, stars would be flung around like pinballs, and the whole universe would become a chaotic mess. As the universe contracts, the CMB would start to heat up. This increasing temperature would be bad news for stars. The coldest stars would be the first to go, unable to radiate away their heat and eventually evaporate like puddles in the summer sun. Then, as the temperature keeps rising, even the hottest and most massive stars would boil away. In the final minutes of the Big Crunch, the universe would become a scorching inferno. The temperature would soar to unimaginable heights, ripping apart atoms and atomic nuclei. The remnants of matter would then be swallowed up by black holes, which would themselves merge and grow, becoming monstrous cosmic vacuum cleaners. Finally, at the moment of the Big Crunch, all matter and energy in the universe would be compressed into an infinitely small and dense point, a singularity. This cataclysmic event would be the end of everything as we know it. But some theories suggest that it could also be the beginning of something new.